We're in New York City at Columbia University with Greene, who's Professor of Physics and Mathematics, author of The Elegant Universe, The Fabric of the Cosmos, and now The Hidden Reality, Parallel Universes and the Deep Laws of the Cosmos, also co-founder with his wife Tracy Day of the World Science Festival. And nice to see you, Brian.
Good to see you.
So, I picked this up at the Bill Hazeltine's book party 2 nights ago. I read it, it's wonderful. Would you like to just do a brief summary of it? I mean, the basic introduction here is there was a time when universe meant all there is, everything, yet in recent years discoveries in physics and cosmology have led a number of scientists to conclude that our universe may be one among many. An infinite number of doppelgangers, each reading this sentence in a distant universe, a multiverse comprising a vast ocean of bubble universes, of which ours is but one, a multiverse that endlessly cycles through time, or one that might be hovering millimeters away yet remains invisible, another in which every possibility allowed by quantum physics is brought to life, or perhaps strangest of all, a multiverse made purely of mathematics. And I remember Bishop Berkeley talking about matter not existing, Samuel Johnson kicking a rock and said, "I refute it thus." I mean, these ideas are out there, aren't they? I mean,
they are out there, but I think the key point that needs to be emphasized is the possibility that we are part of a multiverse, that our universe may be in fact one of many universes, perhaps infinitely many, is not an idea that comes from physicists sitting at their desks and thinking, what crazy idea can I think of now to try to use to describe reality? It doesn't come from that kind of thinking at all. Instead, it comes from physicists sitting at their desks and doing what they have always done, which is develop mathematical theories that try to describe data, that try to describe the things that we can see. And the remarkable thing is, as we have followed the mathematics further and further, we have found that many different ways of thinking about the world, that mathematics bumps into one or another version of the multiverse theme. So the multiverse comes from the math and approaches us. We don't go out and seek it. And that's why it's compelling to take these ideas seriously and see where they lead.
do you find that people have trouble grasping these sorts of ideas when you're out there talking to general audiences? I mean, it's really hard to get your head around.
It's hard to get your head around many of the ideas of modern physics. Even basic quantum mechanics is a difficult subject. I think, however, that people are very receptive to learning about the universe as long as the ideas are presented in an accessible way. I mean, of course, you need to suppress the underlying mathematics, which is what drives us in thinking about these ideas, and focus upon the qualitative insights that the math has provided us. But people are remarkably open-minded about pursuing some very strange ideas because they do come from the attempt to understand the nature of reality, the attempt to understand data, the attempt to understand observations. That gives it a heft and a weight that makes it worthy of understanding.
Now this first page, the chapter 1, where you talk about when you were growing up, each morning when you opened your closet in your room to get your clothes, the one built into its door aligned with the one on the wall, creating a seemingly endless series of reflections of anything situated between them. It was mesmerizing. I delighted in seeing image after image populating the parallel glass planes, extending back as far as the eye could discern. All the reflections seemed to move in unison, but that I knew was a mere limitation of human perception. At a young age, I'd learned of light's finite speed, so in my mind's eye, I'd watched the light's round-trip journeys. So the bob of my head, sweep of my arm silently echoed between the mirrors, each reflected image nudging the next. And this is very pretty writing, very lovely image, by the way. So was that really something that was a driver for this?
Oh, I wouldn't say that that was a driver for the book. That for me really was a reflection, to use a relevant term, that came back to me as I was writing this book. It was more a recognition that this notion of other realities, of other universes, is something that is perhaps less foreign from a qualitative sense than you might think, because, at least in some fanciful sense, it's something that even a young kid could encounter, and I encountered when I was young in a very prosaic setting.
Yeah. So can you do a sort of 101 for us at this point and try and explain how these various ideas fit together. You're string theory.
Yes.
Branes, B-R-A-N-E-S, and so on.
Sure.
It's a sort of a zoo out there.
Yes. Well, this book in particular is an exploration of 9 different ways in which the notion of multiverse has found a place in cutting-edge thinking about theoretical physics. Perhaps the simplest is to recognize that we all know of the Big Bang. The Big Bang is that event which is meant to have brought our universe into existence. But the point that's perhaps less well emphasized is the Big Bang doesn't tell us about what happened at time 0 itself. It only tells us what happened after whatever process brought the universe into existence, and then it says that once the universe was here, it expanded, giving rise to the stars and galaxies that we're familiar with. As we have tried to fill in that gap, to figure out what happened at time 0, to figure out what pushed the universe apart from the get-go, we have come upon a theory called inflationary cosmology, which fills in part of that gap. It tells us that a kind of repulsive gravity is what drove the universe to expand at the beginning. But as we've studied the math of inflationary cosmology, we have found that that Big Bang-like repulsion was not a one-time event. It may have been a many-time event. That is, there may have been many Big Bangs giving rise to many different bubble universes expanding in a much bigger cosmos. So right there you see that our universe may be one of many because there may have been many Big Bangs.
The Big Bang theory, the priest Lemaitre originally, and Einstein, when he first hears about it, says wrong. I mean, ridiculous, right? And it takes Edwin Hubble in 1929 up at Mount Wilson to show that the receding galaxies and so on, expanding universe. Then my understanding from what you've written here is that Lemaitre then met Einstein up there, and Einstein at that point said, no, you were right, it was a beautiful idea.
Yes, that's right. I mean, Einstein was obviously a radical thinker, a revolutionary thinker, but even he did not take seriously some of the mathematical implications of his own theories. So Lemaitre was one of the individuals who had the foresight to recognize that in the math of general relativity was the idea that there might be an expanding universe. Other people, Friedman, Russian physicist, also had this idea some time ago in the 1920s, early 1920s. Einstein resisted this idea for a very simple reason. The universe didn't seem to be dynamic on its largest of scales. All of the data that people had at that time, and even casual observation, would suggest that the universe was eternal and unchanging on the grandest of scales. You know, the stars seemed to be fixed in the night sky. So you're right, when this implication of his own general theory of relativity was brought to his attention, Einstein said, no, I don't believe that. I think the universe is fixed and unchanging. And in fact, what he did was he went back to his own mathematical equations and modified them to ensure that they were compatible with this predisposed notion of an unchanging cosmos. This was a development which Einstein later kind of kicked himself about, because when Hubble showed observation that the universe is expanding, Einstein said, why did I change my mathematics? I should have believed my math. I should have made this prediction. In fact, I should have been the first to have made this prediction of an expanding universe. It shouldn't have been others looking at my math coming to that conclusion.
Yeah, it's an interesting story. A slightly parallel story in your chapter on the inflationary multiverse, where you talk about George Gamow and alpha, and in the 40s, remnant photons from the creation event, in other words, cosmic microwave background radiation, even then, but it somehow takes until, you know, Jim Peebles, Bob Dickey, Penzias and Wilson finally getting a Nobel Prize in 1978 for eavesdropping on the Big Bang for the cosmic background radiation. Again, it's priority, prematurity. Sometimes your ideas are too soon, and
that's exactly right. I mean, the microwave background radiation, this heat left over from the Big Bang that we're all immersed within right now, is the best evidence for the expanding universe model coming from observational physics. And it is a remarkable story that it was in the mid-1940s that people, Gamow and Alpha in particular, realized that this should be an implication of a dynamic universe, of a universe that started with the Big Bang. they couldn't get anyone to take this idea seriously enough to look for these remnant photons from the Big Bang. I mean, think how remarkable that is. We're saying that there are photons in this room right now that come to us from the Big Bang. Look for them. I mean, how more exciting can you get than to find this relic of creation? But from 13.7 billion years ago. But cosmology at that time was a bit of a backwater subject. It seemed very, very speculative. And at that time, quantum physics and understanding the atom and the subatomic particles, that's really where the bulk of attention was. So it got dropped. And then in the early 1960s, another group of insightful scientists led by Robert Dicke came to the same conclusion with Jim Peebles that there should be these photons. They, however, didn't need to convince anyone else to look for them because Dicke himself was not only actually a great theorist but also a great experimentalist. So they started to build the equipment to try to look for these photons. When they get an unexpected phone call from a couple of guys 30 miles down the road at Bell Labs who pretty much accidentally found observational evidence of the Big Bang photons by noise that they couldn't get rid of in an antenna that they were using for various research. You know, Steven Weinberg has a great story about this, not really story, but a great reflection on this. He said, you know, the microwave background radiation was really discovered theoretically in the 1940s, and it took, you know, a dozen or more years before anyone took these ideas seriously. He admonished physicists, you need to take your mathematics more seriously. When your math is telling you something, sometimes you really need to buy into it and have the confidence to look for the implications of that mathematics. And that 12-year hiatus between the initial recognition that the background radiation should be there and its ultimate observation is a real testament to how you need to take the math seriously.
Yeah. What's your, don't mean to trivialize this, but what's your favorite of theory here? I mean, what's
my favorite of the multiverse proposals?
What do you think is the strongest story?
Well, I'd say there's two ways of answering that. The first is, you know, which of these proposals do I think has a chance of being observationally proven first? And of that, I'd put it at the brane multiverse that comes out of string theory. That's this idea that comes out of string theory that all we see may actually be taking place on a three-dimensional membrane. It's easier to think in two dimensions, so the analogy works well. It's as if everything we know about is taking place on a thin slice. I like to think of it as a thin slice of bread that may sit within a larger cosmic loaf, with the other slices of bread, other branes, being other universes. This is a admittedly strange idea, but it's one that may be testable at the Large Hadron Collider in Geneva, Switzerland. There, protons are slammed together at fantastic speed, and it's possible that some of the debris from those collisions could be ejected off of our slice of bread, off of our membrane, and we'd notice that because the debris would take away energy. There'd be less energy in our detectors after the collision than before. So if there is this missing energy signals found at the Large Hadron Collider, that could be evidence that we are living on a brane. And if we are living on a brane, on a slice of bread, there's absolutely no reason to suspect that there other branes aren't out there, that there could be other universes out there in addition to ours. So that's the one I think that has a chance of observational confirmation in the near future, if these ideas are correct.
And that's ideas somewhat associated with Lisa Randall, right?
Lisa Randall did work on aspects of how gravity would behave in these setups, but the idea of the brane world predates any of that work.
Right, okay. Could you explain a little bit about this chapter that's called, I'm looking at this one that's titled, at the end of this chapter here, it says, "Is this science?"
Yes.
And basically, you're saying, look, how do we actually move from inference to explanation, prediction? So how does this work? Could you gloss that for me a little bit?
Well, the one thing that I think is important to recognize about this book is not in some sense a manifesto for the multiverse. It is rather a very considered journey through the possibility that we live in a multiverse, and it extols some of the virtues, but it also highlights some of the failings of our current thinking and tries to ask the difficult questions, which is If you envision that you're one of many universes and you don't have direct access to those other universes, how can you prove these ideas? Have you stepped outside the traditional mold of science, or can these ideas sit comfortably within the traditional way in which we think science should progress? Namely, you have theoretical ideas and you go and test them. And if the ideas survive the testing, you have confidence. If they don't, you throw them away. Can we do that with the multiverse?
And you're saying here, though, in the quarter century I've been working on string theory. I've never seen passions run quite so high, or language turn quite so sharp, as in discussions of string theory's landscape and the multiverse to which it may give rise. And it's clear why. Many see these developments as a battleground for the very soul of science.
Yes.
What do you mean by that?
Well, there is a great deal of controversy surrounding the idea that we may be part of a multiverse, especially within the string theory community, because there are those who think that these ideas have stepped too far beyond testability and therefore have stepped outside of what we'd want to call science, while there are others who think these ideas, however far out they may sound, do have a potential link to observations and therefore do sit within science. That's where the controversy is. And in this chapter in particular, I analyze that in some detail, and I think go a long way toward establishing that the current understanding of the multiverse that we have in our hands does not yet rise to the level where it makes unambiguous testable predictions. That's a problem. However, the chapter also goes on and describes ways in which our understanding of the multiverse could naturally evolve, and the ways in which it must evolve in order to make contact with observation, and shows that, at least in principle, that's possible. So I can give you, a rough sketch of how it is that a theory that talks about realms that we can't see may nevertheless be testable. How would that go? And just to give you a feel for it, if you understand the mathematics of a multiverse well enough, you can come upon a multiverse that may have certain favorable properties. For instance, a multiverse theory that says, yes, all these universes are out there, and in some ways they differ, but if there are features that all of the multiverses share, a definite possibility, then you can look for those properties right here in our universe. For instance, maybe all the multiverses have a certain species of particle with a certain mass and certain charge. You look for that species of particle here. If you don't find it, you have flatly ruled out that multiverse theory, even though you never went to the other universes. Or the multiverse mathematics may show that the vast majority of multiverses have certain properties. Maybe the vast majority have a certain value for the cosmological constant, energy, that we believe suffuses space. If you look for that value of that number and you don't find the number that the vast majority of universes share, your confidence in that proposal will drop. If you find that the number does match the prediction for what the vast majority of universes should have, your confidence will rise.
Could you just unpack the notion of cosmological constant?
Yeah, the cosmological constant is one number that I think is really driving much of the interest today in multiverse scenarios. And what is it? Well, in the late 1990s, two teams of astronomers found something unexpected and remarkable. They found that the universe is not only expanding, this we've known for a long time. Everyone expected, however, the expansion would be slowing down over time. The reason is that gravity is an attractive force. It pulls things inward. So like a ball thrown upward, it goes up slower and slower. Everybody thought the expansion would be slowing down over time. These astronomers found the opposite. They found that the expansion is speeding up over time. It's as if you threw a ball up and it goes up faster and faster and faster. How could that be? Well, something obviously must be pushing the ball upward. Similarly, in the universe, something must be pushing outward, causing the expansion to speed up. And in trying to figure out what that outward push is coming from, people realized that the best explanation as of today actually goes back to Einstein. His so-called cosmological constant is a new term in the equations of general relativity that pushes outwards, a kind of repulsive gravity that comes out of Einstein's mathematics. And we believe that this repulsive gravity comes from an energy suffusing space. That's what the cosmological constant would be, an energy that uniformly suffuses space and gives rise to repulsive gravity. That's what the cosmological constant is. The problem, the puzzle has been when you measure the amount of energy in space that would be responsible for the observed speed up of cosmic expansion, the number's weird. The number is almost bizarrely small. It's a decimal point with 122 zeros and a 1. 10 to the minus 123. We look at that number and we say, how could we ever explain that number? Our equations involve numbers like pi, the square root of 2, 1, negative 1, a half, a quarter. How would you ever start with equations with those numbers and after pages and pages of calculation end up with 10 to the minus 123? That has been the big puzzle. The thing is, a multiverse scenario offers a novel way to explain that number.
Obviously, we didn't evolve in a universe. We didn't evolve hunter-gatherers and so on and so forth to deal with these kinds of numbers. This is an unimaginable territory for most people.
For most people.
I mean, do 9 zeros maybe, but
That's right. But this is a good way of thinking about where the controversy comes from, because there are some physicists who say, don't get so exercised about there being more zeros than we're used to about a fantastically small number. We've been able to explain small numbers in the past, not that small, but don't give up hope. We'll find a way of explaining that small number. Others say, we just can't imagine how we'll ever explain that small number, and that has driven those people to new measures. And the multiverse, it turns out, is a new measure, because if you imagine that all of these different universes that are out there have some amount of this cosmological constant, some amount of this dark energy suffusing space, and if the amount varies from universe to universe, you have a new explanatory framework. You can say, I'm not going to try to explain the number from first principles, from a very detailed mathematical calculation. I simply look out at the multiverse and I see over there dark energy value 0.0001. 0.0001 in that universe, 0.00001 in that universe. And if I look at enough universes, sooner or later, one of them will have the small value that we've observed. That's just how things would turn out by a random distribution of different values of the cosmological constant. So why do we have the small value that we see? Well, randomly, some universe has that small value. And to cap off the argument, in universes where the dark energy value is too big, larger than what we see, the conditions aren't hospitable to our form of life. So we don't find ourselves in the universe where the cosmological constant is 0.1 because that universe has so much repulsive gravity that galaxies don't form. And without galaxies, there aren't planets probably. Without planets, there aren't people. So we live in that universe where the cosmological constant is small enough to be compatible with us being there. And that's this line of argument. Some scientists don't like that approach.
You talk about dark energy, dark matter. I was having a conversation with Neil Tyson the other day.
Yes.
And he'd just done a Colbert show and so on. There was a Bill O'Reilly had been saying that the sun goes up, sun goes down, tides go out, and nobody knows how that works. There must be a God. And Neil went on and tried to explain how tides work.
The tides? No,
the,
we understand the tides
moon,
pretty well.
Invoking the moon.
It is the moon. My friend Mr. Tyson is right on the mark.
But in the course of that discussion, that conversation, it was also pointed out that we actually only know about 4% of what's going on in the universe. 96%
yes.
is just a mystery. So you can understand why somebody on the street might say, why are you telling all these other stories here if you only know 4% of what's going on? I mean,
well, in fact, we are telling these stories to try to get a firmer handle on the other 96%. Because I think the thing that's really important to bear in mind is, when we say that we understand 4% of the universe, what we really mean by that is 4% of the universe is made up of the stuff that we are directly familiar with because it makes us up, and the stuff, tables and chairs in the world around us. Protons, neutrons, electrons, those kind of particles make up 4% of the mass of the universe. Remarkably, we can tell you how much the rest of the universe weighs. That's a pretty vital and detailed piece of information. We can tell you what that other 96% of the universe does in terms of the kind of gravity that it exerts, but we're still struggling to pinpoint exactly where it comes from and explain why it has the particular value in terms of the mass component of the universe that it does. So the resort to a multiverse explanation is an attempt to give a real detailed explanation of why it is that we see a certain amount of that dark energy, why we see a certain percentage of the universe being made up of that dark energy. It's not an attempt to run from the issue. It's an attempt to answer the issue.
Okay, you've got a couple of nice things in here that I wonder if, I'm not sure if you can do these quickly or not. One of them is the story of Hugh Everett and,
yes.
and the whole, and then connected to that, you have some very nice illustrations here and a nice idea, which is to do with Schrödinger's work, and you set it up nicely for New York with looking for electrons in strawberry fields at John Lennon's Memorial in Central Park and then Grant's tomb in Riverside
right.
Park. What's all that about?
Well, this is the subject of quantum mechanics. Yeah. And the basic new idea of quantum mechanics is that whereas Newton would have said, tell me the state of the universe right now and I'll predict the state of the universe tomorrow, and I'll tell you it with absolute certainty how things will be tomorrow if you tell me with certainty how things are today. Quantum theory says that's the wrong approach to describing how physics works. Quantum theory says the best you can ever do is predict the probability that things will turn out one way or another. Strange new idea in the fundamental laws of physics. So for instance, if you are looking at the position of an electron, quantum theory says the best you can do, for example, is to say there's a 50% chance the electron is here and a 50% chance that it's there. You can't do any better than that in certain situations. And that is an old idea that has long been tested. Every physicist buys into it. But there's a remaining puzzle that gets less airtime, which is this. If there's a 50% chance the electron is there and a 50% chance that it's there, you do the experiment and you always find it either there or there. You never find it sort of in both. The question is, how do you go from this probabilistic haze where the particle could be here or there to the single definite reality that your observations reveal? How do you go from probability to definite reality? Nobody has an answer to that even today. Hugh Everett, many years ago, suggested that maybe the answer goes like this. If the electron can be here and here, then when you do the measurement, the world kind of splits. The universe splits. And in one universe, you find the electron here, and in another universe is another copy of you who finds it over there. Parallel universes emerging from quantum physics. That's the idea of the quantum mechanical multiverse. And in the book, I try to explain these ideas at a level of detail, not with mathematics, but a level of qualitative detail that most people don't take on the subject. And I do use an example of an electron being in New York and being possibly at the John Lennon Memorial and possibly at Grant's tomb, and using that to illustrate some of these ideas of Hugh Everett and the many worlds of quantum physics.
There's a lot of stuff about Einstein as well in here. You probably read Alan Lightman's novel, Einstein's Dream.
Yes, sure.
Have you ever thought about writing a novel?
You know, in the back of my mind, it would be fun to do a novel. I did one short work of fiction for kids, a rewriting of the myth of Icarus called Icarus at the Edge of Time, where the boy doesn't go to the sun but goes to a black hole, and the physics of general relativity then determines how the story unfolds. But it's a very short work. You know, it's a few thousand words. It would be fun to do a novel, but haven't embarked on that yet.
Background, born in New York City?
Yes, I was born in New York and grew up on 81st Street, actually right across from the Hayden Planetarium. And that's where I would go on rainy days. My mother would send me there to get me out of her hair when we had to stay home for any reason. So that was really my stomping ground.
So, like Neil, the universe called.
Well, I wouldn't use the dramatic terms that perhaps Neil does, but you know, it was a fun place to hang out.
But what was the interest in science? What were your parents doing at this point?
Well, my dad was a composer and a vocal coach, a voice teacher. So he would be, you know, writing music and teaching singing. And my mom actually worked for a veterinarian a few blocks from the house down on 74th Street. So it was really grounded in the most basic things of, you know, taking care of animals, and that's what the doctor did, and she got into real estate through him. And my dad was kind of floating in the more artistic realms of, you know, trying to, you know, understand truth and reality through music.
So, where was the impetus to science then, do you think?
Well,
teacher, a book?
Definitely my dad. My dad was a high school dropout. I mean, he liked to call himself an SPhD, a Seward Park High School dropout. And even though he didn't have formal education, he loved science. So he would introduce him to the ideas of stars and atoms, you know, in a qualitative way. He didn't have any technical training, but it was enough to get me very excited.
And you went to Stuyvesant High?
I went to Stuyvesant High School, that's right.
As did Lisa Randall, of course.
Yeah, there, you know, a lot of scientists pass through the corridors of Stuyvesant High School. It really is a wonderful training ground for those who were serious at a young age about science.
Yeah. Well, I'm forgetting the name now, but isn't there a rather legendary teacher who was a math teacher at Stuyvesant High?
You know, there were a lot of great teachers. I'm not sure, you know, which one you have in mind in particular, but you know, they took it very, very seriously and were good about getting kids excited.
And then?
From high school, I was college at Harvard, and was a graduate student at Oxford.
Right.
Where
this is in physics, or?
It was in physics, although I started at Oxford in mathematics with Roger Penrose, but his focus at that time was, you know, even more mathematical than my taste at that time was, so I shifted to the physics department.
The urge to write books and end up doing PBS series and so on and so forth, how did that evolve, and what was the story on that, the trajectory there?
Well, as I got ever deeper into some of these subjects, I would have conversations with people now and then, and I could sense there was this sort of untapped reservoir of interest on the part of people who loved the subject, loved the idea of the far-out nature of some of the science we were studying, but didn't have the technical training to really read any of the papers. So little by little, I got ever more excited about bringing these ideas to a broader audience, and wrote my first book back in 96, 97, 98, The Elegant Universe, and I didn't know if it would reach many people, but when it did, and when there was an enthusiastic outpouring for that book, it got me ever more excited to spend a substantial fraction of my time bringing science to general audiences.
Hmm. So the point, your mother was a veterinarian originally?
She was an assistant to a veterinarian. She too, you know, finished high school but didn't finish college, and didn't have, you know, the academic training, but has a lot of street smarts. And I think that, you know, is an important balance to the pursuits that take you as far away from streets as you could imagine, you know, multiple universes.
Yeah. One of the other things that turns up in any article about you, of course, is the fact that you're a vegan.
Yes.
Do you want to sort of, how did that come about?
Well, you know, I became a vegetarian at 9, largely because of my mom's cooking. You know, she made spare ribs once when I was 9, and finally the link between meat and animals became abundantly clear with that meal, and I never had meat again after that. But I did, for a while, have other things like dairy and so forth, until I went to an animal sanctuary, I don't know, about 15 years ago in upstate New York when I was at Cornell. Learned about the dairy industry, was happy to have not known about those things, and perhaps wish I hadn't gone to that sanctuary on that fateful day, because afterwards I just couldn't have any more dairy, and that was that. So.
Yeah, it's tough, isn't it, though? I mean, this was John Robbins' book.
You know, it is tough. It is tough, but it's getting easier. I think there's a lot more people who are pursuing this kind of way of life. So you go to restaurants and supermarkets now, it's much easier to get things than it was 15 years ago.
The other thing that I wanted to raise with you is on a slightly different point. We just mentioned this. Perhaps it was in the last book, that there's not much in here about entanglement,
yes,
which has become a very hot topic.
Right.
Anton Zeilinger has a new book out. Louisa Gilder, of course, did that very nice Age of Entanglement book.
Yep.
A lot of this stuff goes back to John Stuart Bell.
Yes.
What's your position? But can you get anything from entanglement ideas that maps onto you know, Spinozistic or Buddhist visions of how the universe is?
Sort of some pantheistic way of thinking about things? Only vaguely. I mean, I think entanglement was the central theme of my second book, Fabric of the Cosmos, and that's more or less why it doesn't play any role here, and also it hasn't really had much of an impact on some of these multiverse ideas. But yes, entanglement does suggest a kind of interconnectivity between widely separated objects that does, at least in words, have some resonance with ideas that do come out of certain approaches that generally are thought of as non-scientific, but perhaps have some link through these ideas. My own feeling about entanglement is that it's one of the most remarkable established ideas of science that we've come upon in the last century. the notion that something over here can be linked to something over there through empty space is, spectacularly odd. And the interesting thing is the only way around, the only loophole in the traditional interpretation that there are non-local influences doing something here, affecting something over here, the only way around that I'm aware of is the multiverse that comes out of quantum physics. So the many worlds interpretation does offer you a way around this non-local interpretation, but many people think that the multiverse is yet stranger than non-locality. So if they're not willing to buy non-locality, many people are saying, I don't want to go near the idea of other universes. That's even harder for some people to accept. So in many ways, I would say it's a matter of picking your poison. Do you want to accept that what you do over here can affect something over there? Or do you want to accept that there are many universes coming out of quantum physics? Those are the two explanations for the data that have a chance of standing up to scrutiny. There are those, and in fact I'm one of them, who find other problems with the many worlds interpretation of quantum physics, and that's really what I focus on in that chapter.
Yeah, I suppose, so this all goes back to some extent what we've just been talking about, to Einstein, Podolsky, Rosen,
Yes.
to Einstein being worried about spooky action to distance.
Yeah, Einstein was really the first person to point out this possibility.
David Bohm's work later and so on.
That's right, and others who thought, well, Einstein, you're just talking about metaphysics. You're bothered by some idea that we'll never be able to test. And then it was John Bell who said, whoa, you can test it. Here's how. And then other people like Alan Aspect and others finally, and Clauser did test some of these ideas and showed that the weirdness that Einstein was pointing out, the spooky action at a distance that you're pointing toward, was supported by not just the theory, but by the data. That was a remarkable achievement.
I suppose that two of the most influential writers of the last century in legal terms, justice terms. One was John Rawls, obviously, and the other, taking a completely opposite view, was Robert Nozick.
Yep.
Wonderful philosopher. Could you tell the story, your Robert Nozick story?
Yeah, sure, happy to. When I was a freshman in college, I took a philosophy course with Robert Nozick and was really fascinated by the subject, and I hung around after class often to just chat with him about things. And one day he asked me what I was interested in, and I said, well, I want to figure out the unified theory that'll put gravity and quantum mechanics together, sort of this naive little freshman talking big. And, nicely he didn't clamp down on me for the hubris of it all, but simply asked, what if you found the unified theory? Would that answer all your questions? Because you'd still be left wondering, why that theory and not another theory? And at that point, I was sort of aware of that issue and said, that's right, sometimes you just sort of have to accept some things as given. And he said, no, you don't. Because he was writing a book at that time called Philosophical Explanations, which was really the basis of the course that he was teaching us. And he had come upon an interesting idea called the principle of fecundity, he called it. And this was an approach that would leave no answers without justification. He didn't want it to be the case that you answered a question and you just said, well, the reason for this answer is, it just is. He wanted to avoid all of those kind of just is explanations. How? He imagined a multiverse. He imagined that the universe had many, many universes. In fact, every logically possible universe would be out there. And then you'd never have to say why these laws as opposed to those, because all laws would be realized in some or another universe. And the laws that you see would just be the ones that were compatible with your living in a universe that allowed you to see those laws. So it was a remarkably prescient idea, this notion of there being many universes, realizing, in fact, all possible realities. The problem for somebody like me, a physicist, is there's no way for that multiverse that I can think of to ever disprove it. Again, it comes back to the central idea. You can't believe any of this stuff unless you've got experimental verification. You won't be able to prove or disprove Nozick's idea, however, because no matter what data you see, presumably it's logically sensible, and therefore it's data that's compatible with one or another universe that's out there. There's no data where you'd say, oh, that's incompatible with this theory. It would have to be logically nonsensical, and at that point, if we get logically nonsensical data, we should throw in the towel. Our whole approach to understand the universe will have failed.
In terms of communication of science, obviously with your wife Tracy, you run the World Science Festival. You also do a lot of communication, obviously, in terms of the books and PBS stuff. There was also a nice op-ed that you wrote for the New York Times. The title of that was "Put a Little Science in Your Life." Yes. And you were talking about getting a letter from an American soldier in Iraq saying that it was physically exhausting, emotionally debilitating, but even there, a book that you'd written had become a kind of a lifeline for him. It was a book about science. That must have been very reassuring and so on. So you're writing here basically a valentine to science and to the communication of science. Would you put that together with a question I ask a lot of people, which is that when his administration took over, President Obama said that they would try and restore science to its rightful place. What do you think is the rightful place of science?
Well, I think the rightful place of science is right alongside the other aspects of culture that we consider indispensable. We consider literature, music, theater, film, dance, performance, all of these aspects of life we consider indispensable parts of our cultural makeup. If you were to go to people and say, we have decided to eliminate films, we have decided to eliminate literature, it would be unthinkable. And I think that's the way we need to think about science. It is a vital part of culture. It is a vital part of what makes life worth living. The problem is most people think of science as, oh yeah, a subject that they took in school, got through the exam, and then once they cross the threshold of the science lab, they leave it behind. And that's not what science is. Science is a perspective. It's an outlook. It's the way you rationally evaluate the world around you to come to some sense of what's true. It's hard to imagine anything more important than that. Now, there are many ways of approaching truth. You can approach truth through literature, through art, through music, and that's wonderful. But all these different approaches are illuminating aspects of some fundamental reality that science has a wonderful capacity to reveal in its most stark and its most breathtaking form. And that's how we need to think about science.
You have students here?
Yes.
What's the advice you give to you? I'm thinking about Peter Medawar's book, Advice to a Young Scientist. What advice do you give young scientists?
Well, it really depends case by case. I think, some students are very practically minded and worried about their career, about their job. And there was a time when I would advise students, don't worry about that. Just do what you love, and whatever happens will happen. As I've gotten older, I think I've become a little more practically minded myself, especially when students go out into the world after working very hard and they can't get a job. So I now try to balance perspective between doing what you love, doing what fires you up, and also recognizing that some students are better equipped to succeed in these esoteric and abstract fields than others. So part of what I try to do is now gear the course of study a little bit more finely to the capacities and the interests of students than in the past, where I just said, if you love it, do it. I think that's only partly good advice. You also have to do something that aligns with your capacities, your abilities, and what your ultimate goals are.
Well, we're a couple of days away, one day away from Francis Bacon's 450th birthday, by the way, January the 22nd. And obviously, a lot of the things he wrote became the impetus for the formation of the Royal Society, which had its 350th anniversary last year.
Yep.
These communities of scholars, these merchants of light that we've talked about before, obviously had an enormous impact. You've written about a lot of these historical characters as well in your other books. Here's a question I like to ask people. If I gave you a time travel token, which seems very appropriate for you, and you could bring anybody from any period of history, whatever, to your dinner table and ask them some questions, have a conversation, is there anybody that you'd really like to get to come to dinner?
Well, honestly, what I'd really like to do with that token is not necessarily invite people from the past. I'd like to invite the great scientists from the future, because that, to me, is where the astounding new insights obviously will be.
Was I right about the multiverse?
Or even, string theory right? Or,
yeah.
do we now understand where time came from?
Yeah.
You know, these are the kinds of questions that I think we'll have a handle on at some point in the future that we don't know now. But, you know, looking to the past, I mean, the obvious characters are the ones that have had the greatest impact on the way we think about things. So, you know, I'd love to have Newton in the room, love to have Galileo in the room. Aristotle, yeah, that'd be pretty fun too. You know, who would pass up having Einstein? Maxwell, sure. So having, you know, these great minds from the past come to grips with what we've learned since they left us, I think would be spectacularly interesting. And I can't imagine that they wouldn't have some great ideas that would propel us in directions that perhaps we're not pursuing right now.
Yeah. Towards the end of the book, you talk about branes, but this time with an I. In other words,
yes,
stuff at the end of your spinal column there. What's your thinking on that? What's the
well, the penultimate chapter is a more fanciful chapter that steps a little bit outside of the ideas that have emerged from mathematical study of string theory or cosmology or quantum physics, and asks whether you might have multiple universes that are of a different sort, simulated universes, universes like the Matrix, universes that take place within a computer. And I find that an interesting question in the same way that I think, you know, everybody who loved the Matrix finds that interesting question. But it was also an interesting question to ask a deeper philosophical question, which is, what is the nature of mathematics? Is mathematics a description of reality, or is it reality? Because if you had a reality that was simulated on a computer, where there were really individuals who were sentient, who were thinking that the reality around them is as real as the reality that we think ours is, but yet they're in a computer, open the hood of the computer and what's going on? Mathematical calculations are driving the computer from step to step to step. So could pure mathematics create a reality that is as believable to its inhabitants as this reality is to ours? And perhaps is our reality just mathematically generated? That's a question that people have asked for a long time. I think the computer provides a nice concrete way of framing it. Because if Dr. Johnson that you were talking about earlier, you know, if he kicks that stone and feels it kick back and says, I refute it thus, this is my proof that reality is real. If that kick is happening inside a computer, inside a simulation, then that proof of the reality of the environment would be actually a proof of the reality that mathematics creates an environment that makes you think that reality is what you see. That would be a very spectacular development if we could establish this link of mathematics not just as a vibrant tool for describing reality, but mathematics as being reality.
What are you optimistic about?
I'm optimistic about our capacity to make progress at addressing some of the deep, big questions that our species has asked for thousands of years. Across cultures, we have asked in one form or another, how did the universe begin? There are so many creation stories. They come from the urge to understand our origin. In physics, in cosmology, we're getting closer to answers to that. And if I had that time travel token, I do believe that if we bring scientists from 100, 500, 1,000 years from now, we will be able to answer that question with a certainty that will be enormously gratifying.
See, on page 309 here, you've got a table which says summary of various versions of parallel universes: quilted multiverse, inflationary multiverse, brane multiverse, cyclic multiverse, landscape, quantum, holographic, simulated, and ultimate. Do you have any bets on?
If I was going to put bets on it, I would certainly bet on the brane multiverse. I would also potentially put bets on the inflationary multiverse. Inflationary cosmology has been wonderful at describing cosmic microwave background data. It gives rise naturally to this multiverse of many, many bubble universes, each undergoing their own Big Bang-like expansion. There are holes in the inflationary multiverse, mathematical ones that we need to fill. We've not yet filled them. I think that there's a chance that we will, and if we do, then I'd put a significant bet on that multiverse as being real.
Have you ever considered, did you ever consider doing anything other than being a scientist? Are you a frustrated opera singer or something?
Well, when I was a little kid, I wanted to be a professional bowler.
Really?
But I never progressed well enough to realize that life dream. But if I was seriously going to think about doing something else, I think music is what it would be. You know, I don't really play anything. My dad, as I said, was a composer. I find music as this way to transcend everyday reality in a very visceral manner, and frankly, that's what I think this physics does. It's speaking to a reality that transcends the everyday. So that's the kind of pursuit, something that rises above the everyday, that I find most compelling.
Yeah, I noticed, I was just looking here from my notes, there was a couple of places. You mentioned Mahler's Eighth in one place, for example, when you were talking about
Yes.
bringing Newton up to speed and so on.
Yes.
So there's lots of you
References,
put
sure,
musical
yeah.
references
Yeah.
in there as well. Tell us about the forthcoming. It's the forthcoming World Science Festival.
Oh, the World Science Festival,
which again
yes.
will integrate a lot deal of music, performance, dance.
Always, yeah. The World Science Festival does try to bring together the worlds of art and science in a natural and organic and powerful way. So the 2011 festival will be June 1st to 5th, I think, and we'll have a lot of works in the art that speak to science, but also a lot of great science programs. The program is not yet settled, but they're apparently underway now is plans to have a program on digital physics along the lines of what we were just discussing. Is the universe a big computer executing some cosmic computer program that we call the laws of physics? That will be one of the programs that's discussed. There will be a program on the dark stuff, dark energy and dark matter. We'll have a prominent role.
96%.
That's right. We'll be discussing the 96% of the universe that we don't quite know what it is. And there's a lot of great programs also in focusing on the brain and the mind.
Well, we look forward to it immensely, and thanks for the conversation.
My pleasure. Thank you.
Good luck with it. Thanks.